Hi folks, this is the third tutorial that I'm preparing for analyzing a frame structure. Particularly, I'm interested in the modal analysis of a frame structure. Roughly, the problem that we have is shown here because in tutorial 1, which was actually taken from this reference, the dimensions were different and also uh, the the column on the right hand side was also clamped. That was tutorial 1. There, although the size was a little bit different, but the process is the same. There, what I did is draw this frame structure as a two-dimensional sketch in CATIA, and once I exited that, I joined that sketch. Now, when you join a sketch and you mesh it, at the juncture between the beam, horizontal beam, and the vertical column, you have a common node, the same node. When you join it, by default, it makes a single node connecting the beam to the column. Same thing on the right-hand side. And of course, there won't be an issue. You can solve a static problem, you can solve a modal problem, etc. In tutorial 2, I did not actually draw that thing in a sketch. What I did, I created 3 wireframe lines in space. 2 vertical ones, which are representing the column, and a horizontal line, which represented the beam. Now, when you mesh those things, in tutorial 2, what I did, I asked for any 2 nodes which are within a certain tolerance of each other to be merged. So when it comes to meshing the vertical column, you get a certain node on the top, and when you mesh the horizontal beam, you get another node on the top. But because I asked for the 2 nodes to be merged using that particular checkbox, it essentially uh, created this common single node at the junction between the beam and the column. And what I mentioned in tutorial 2 is that if you don't use that checkbox, there will be duplicate nodes, a node a node from the beam on the top, and a different node from the from the column on the left hand side or the right hand side, and these are different node numbers, and you have to do something about it, and that is called high connection. So the purpose of this tutorial is to actually do a tight connection between these this discrepancy that we have from the beam to the column at the junction. Now that is the way this problem is done in CAE in the reference shown below. Okay, so here's the situation. We are assuming, as in tutorials 1 and 2, the beam is rigid. And of course, we're going to replace it with a rigid beam and, of course, a lumped mass. Lumped mass of, in this case, 500 kilogram. And then we have to create high connection between the horizontal beam and the vertical column, both on the left and on the right side. And you see it here in the tree. So in order to create the tie connection, you have to specify the 2 edges that you want to be tied together. One of them is the main, the other one is the secondary. So notice that this particular one is concerning tie 1 for the left side of the structure, and tie 2 is going to be the same, which I'm not showing here. But it is important how you select the main. For example, the main is going to be the beam, the rigid one, and the secondary is going to be this vertical column, which is flexible. Okay. Now, same thing for the tie 2. When you create the tie 2 for this connection on the right side, you for the main you select the beam, and for the secondary you select the right column. Okay. And you also have to make sure that the degrees of freedom are transferred from one side to the other side. So this is very important. and we have to do that. Now, we are assuming that these are same material properties that we'll use in tutorial 2, but I'm going to reduce, as it happened in tutorial 2, we're going to reduce the density of these columns by a factor of 10,000. That means that their mass is not going to participate in calculating natural frequency. It's just this lumped mass on the top is going to appear. Okay. The cross sections are rectangular or square actually. So these are the dimensions, and the answers that we got in tutorial 2 coming from that YouTube reference is given here. We're going to be comparing our results there. In that YouTube tutorial, the fellow is using B32, but B32 is a three-dimensional quadratic element, two-noded quadratic element, but that is not available in uh, uh, in 3D experience. So I had to do that. I had to use B31, but the results are going to be fairly close. And you saw this thing in tutorial 2, but you're going to see it again. So when you create rigid connection, then you have to have a reference point associated with it, and we're going to put the lumped mass at that reference point. That's why when you look at the point inertia or lumped mass, the support is the same as the support for the rigid connection. Okay, and this is the checkbox that I was talking about in tutorial 2. I actually use this checkbox, and when you use this checkbox, these connections, these nodes on the top and on the vertical side, they're going to get merged together. There'll be a single node here, but if you don't, there's going to be a different node number if you come from the right side, or if you go from the bottom, there's going to be different node, and this is where time coming into the picture. Okay, so let's go ahead and do this. Uh, what I'm going to do is I will create the geometry with four points, and then an extra point, which is going to be the uh, for the orientation point, because the cross section is not circular. All right, so let's start doing this. First point is going to be 0, 0, 0. Let me cancel that. Control Z. I want to get through these. Okay, let's try it again. So point first is going to be 0, 0, 0. Another one, which is going to be 6,000 millimeter up. Let's fit it. There we are. It's right there. You can see that. Another one, which is 5,000 to the right of this, under essential. Another point, which is 5,000 to the right. It's right there. You can see that. And the last one is going to be height of 2,000. Okay, so we have our 4 points, 1, 2, 3, and 4. And then I'm going to create an orientation point because the cross section is non-circular. So what I'm going to do is for the X, I'm going to make 1,000 so that it's kind of a distance away so that I can see it. Not a big deal. Now we're going to create our lines. So the first line is going to go from this point to that point. Okay. Then it's going to go from this point to this point. Okay. And then from here to here, and okay, and then cancel. So basically this is the left vertical column, right vertical column, and this is the B. Now these points play absolutely no role except for this orientation point, so I'm going to hide them because you don't want to accidentally put the restraint and boundary condition and stuff like that on these points. You can delete it, but you can hide them. All right. Now, let us apply create material properties. So we're going to go to uh, tools. I'm going to create a material. Today is February 5, 2024. So modal frame, call it frame. All right. So it's going to get a template is going to be created here. Once it appears right there, I'm going to say apply, and I can close these things, apply to that part. And now we're going to input the values. So we go here, double click. Structural, because we're doing a dynamic problem, we need to specify the density, but this is the dummy density, which is 0.24, 10,000 times smaller than what that column's density is. Okay, good. And then we're going to go to ABAQUS multiphysics, mechanical, elasticity, elastic. This was 30 million GPA or 30 GPA, 30 GPA, 30 million MPa. No, sorry, 30 GPA. That's what it is. And the Poisson ratio is 0.22. Okay, so that takes care of the material. Let me quickly save this thing. All right. So as far as the model is concerned, this is all done. Let me hide these things also. So we go to the meshing application, which is called structural model creation, MTFEM. All right. And now under the meshing, we're going to do beam meshing. I select this one and notice that the size of the mesh is 200 millimeter as I did in tutorials 1 and 2. And I'm not checking this box because I don't want the top node of this to be merged with the horizontal, the node from the horizontal member. I don't want to do that. You say, okay, mesh, okay. Another one for the horizontal one, mesh, okay. Another one for the vertical one, and mesh, and okay. Okay, good. Then I'm going to apply properties. So because this is a beam, so we go properties. First, the profile of the cross section. So beam profile. The first one, I'm going to call it the left vertical, left column, left column. And the cross section is rectangular. The size is 150 millimeters, 150 by 150. Let's just make sure that this is correct. Yeah, left column 150 by 150. Good. We say okay. All right. And then we're going to do another one. And this one is going to be right column. Maybe I'll call it beam. How about that? Horizontal beam. Horizontal beam. Okay, so again, it's rectangular, and the size is 100 millimeter by 100 millimeter. Okay, and finally the right column. Notice that we are creating the profiles here, and another one. I'll call it the right column. Right column. Okay, and rectangular, and the size is 225 by 225. Very good. Okay. Now that we have created the profiles, we can go and create the beam section. This one is the left one. Okay, so that is going to be, I can call it beams, I can call it, what do I call it actually, left column, just so that I can remember what these things are if needed. And for the support, we already selected it. For the profile, it's going to be left column profile. And for orientation point, I use this, okay? So say fine. Okay, notice that the first one is created. Let's do another one. I'll do the horizontal beam next. So this is going to be the, let me call this thing horizontal beam. Okay. Yeah. And for the support, it's going to be this. And for the cross section, it's going to be horizontal beam. And for the orientation point, same point. Okay. And finally, that guy, I'm going to call it uh, right, right, right column, right, right column. Okay. And the profile is going to be right column profile, which is size 225 by 225, and orientation, same point. Okay. Good. Incidentally, if you want to see these cross sections, so all you have to do is to say display under display preferences. Instead of none, you can say solid. You can see that. So this is the biggest one, 225 by 225. This is the smallest one, 100 by 100, and this was 150 by 150. But I don't want to see it. I just close it. Or I can. Okay. So if I want to, if I don't want to see that, just say none. Good. Save everything. All right. Then we're going to create our rigid connection here. So we go to connections. This is the rigid connection. It says the support is this support. You can see that this horizontal beam is going to be rigid. And for the support too, I have to create a point. For example, I can create a point here. I'm going to do that in the middle and use that. So put the cursor there, right click, create a support, and it's a create a point. And it says, okay, you want to create a point? Select your thing that you want to create it on. So I select this. It says, okay, do you want to specify the coordinate, or do you want to do it on the curve? I'll do it on the curve. It's easier. And say which curve? The curve is right here. And we're going to do ratio of the curve length 0.5, which is halfway in the middle. I could have put the coordinates if you wanted to. Doesn't matter. That 0.5, 0.5. And then we say okay. And then obviously here it took 0.6. That 0.6 is precisely the point that we just created, right there. Okay. And we say fine. It's a kinematic coupling type. Fine. And now we're gonna put our lumped mass at that location. So under abstraction, uh, it's called in point inertia. It says where it's going to be on that 0.6, and the value of it is 500. This was all uh, uh, in the slides. Okay, good. All right. Now comes the moment of truth. As far as first of all, do we have different nodes here? How do we see that? That's easy. You go to display. You go to display. Let me update. If I don't update, it's going to say, well, I updated. Okay, so see, it says node numbering visualization. It says numbering is out of date. Please update. See, fine. Okay, I'm going to update first. Then I click on that. No problem. Okay. Let me hide the part. So right click visibility manager. I don't want to see my part. I want to see the elements. So if you put the cursor up here, let me zoom in. If you put the cursor up here, it says node number 2. But if you come from this side, it says node number 32. These were not merged. In tutorial 2, they were merged, and there was a single node number there. And the same thing on the other side. So we are guaranteed that these are actually different node numbers. Okay, good. So what we have to do is we go to connections. Right here it says tie. And remember, I said that make sure that you select for the main, let's call it main line, uh, the horizontal one. Okay. Now, if you're having a hard time selecting it, let's hide the mesh. Get the part here, right there. So for the main geometry, select the horizontal one, and for the secondary one, left column. Make sure these are checked. Make sure the rotational degrees of freedom are transferred. And if there is any adjustment to be done, you say okay. Incidentally, if you inadvertently maybe picked it other order, you can always flip them here. But that's good. That's good. So that's for the first tie connection, which is under engineering connection. You can see that tie one right there, and then repeat that. Where's that? Repeat that for tie two. For the main, you select once again that horizontal beam. For the secondary, the vertical column on the right. These are checked, and we say okay. So tie one and tie two. So that's what these slides were referring to right here. This was tie one, but okay, good. Now we are guaranteed that this node 30, I think it was 32 and 2, they move together. That's really what it boils down to. Okay, so we're pretty much done here. Now we're going to go to, incidentally, this step I forgot to do in tutorial 2, and then I had to go back and do it uh, properly. Okay, so anyway, you go here, you go to structural scenario creation. We use our finite element model. And we're going to do a frequency analysis. So under procedure, we go to frequency analysis. Oh, where is that? Right here. We'll get the first 10 node, 10 modes. We say fine. We go apply restraints here. So we go to boundary conditions. Uh, Clamped here, but I use fixed displacement, all 6 degrees of freedom. And make sure that those points were hidden so that you don't put it on those points, because those are not geometrical entities. And then we say okay. And then on this side, you do the same thing, except that it's pinned. So we have X, Y, Z translation, and that's pretty much it. Let's do a quick save here. And I think we should be good. Okay. Let's go to simulation. First, a quick model and scenario check. I don't anticipate any problems. Then we're going to do a simulation check. And finally, if there are no issues, we're going to run it. The only subtle issue here, in my opinion, is the order that you have to select that main line, the horizontal beam, and the secondary line, which is the vertical column on the left and right side. Because I'll show you, if you flip those and you try to run it, you're going to get an error message. We'll do that at the end. Good. And finally, we're going to run it. And if you look at the frequencies, you should be getting those 10 frequencies that were shown here in the right here in this table. 6 of them. Okay, extracting results. And okay, it's almost done. Good. And these things are exactly these. Don't let it fool you, because the reason that they're so close is because the solver is the same. We have Abacus solver. There's slight differences. The differences are the fact that this fellow is using the quadratic element. I don't have it in 3D experience, so I'm using linear element. Now, if you want to see the mode shapes, you go to displacement, for example. This is the first mode shape, second mode shape, etc., etc. And if you want to see the three-dimensional view, in a sense, so you go to view, uh, sorry, not view, on the display, and if you click on this, if you click on rendering setting, actually, what I wanted to do, that's not what I meant. Click on this on the screen on this deformation. Look at the third tab, and instead of line, beam style line, see profile. Yeah, profile, apply. I mean, it's just for visual purposes. It adds nothing to the value of this. But here are the other modes of the vibration. Now, let's go ahead and flip the order of that selection. So if you go back, if you go back to our model and check the uh, engineering connections, if you click on the tie, and I'm just going to flip one of them. Okay, you can flip both, but it's going to cause the same problem. I'm just going to flip one of them. So in a sense, for the primary, I selected the vertical one. For the secondary, I've selected the horizontal one. That's going to cause a problem. Okay, you see. So I didn't even bother doing the other one. Even this will cause a problem. Go back to the scenario and run it, and you're going to get all kinds of crazy error messages, and that is the problem. I will be doing a few more uh, segments on these frame structures. Okay, we're going to go to a three bay uh, a 3-bay shear frame, and then a multi-story frame building. Now here we can see that error. That's, we know what the issue is. Unfortunately, the description here is not always very helpful, but yeah. So the cue here is go back there, flip these so that this becomes the primary and this becomes the secondary. And that's pretty much it. This takes care of the tutorial 3. Good luck.